So thanks everyone for being here. Didn't expect so many people, but it's nice to see you all. This talk is going to be about using Python to make sense of system traces. So I'm going to be showing how we can capture kernel traces and also user space application traces and work with them with Python. My name is Jérémie Galarneau, and I maintain LTTng tools, which is part of the LTTng tracer infrastructure, and Babeltrace, which is a trace manipulation framework, and also the default text reader of LTTng traces. I'm going to start with a brief introduction about what is tracing and how it differs from logging, which you may know. And then I'm going to present LTTng, since that's what I'm going to be using for the demos. And really then we'll see how we can use Python to work with those traces. Hopefully we'll have some time for a Q&A. So the question I get all the time is, isn't tracing just another fancy name for logging? Yes and no. Tracers are not completely unlike loggers. Both try to save enough information so that you can make sense of what was happening in an application or on the system when things went south. But while they both try to cater to developers, admins, and users, tracers are skewed towards the developers and the admins, since we save low-level events most of the time. In both cases, most of the work is spent in trying to find a careful balance between being too verbose, affecting the performance application, and then producing logs that are not really useful. If you end up with a couple gigabyte log and you're looking for that one error that happened sometime, it's basically useless. So loggers are going to be using logging levels. In tracers, typically, you'll be able to enable selectively a couple of events. Tracers, as I mentioned before, the big difference is that we focus on low-level events. The best example I can give is for a kernel tracer that would be syscalls, scheduling events, so a process being scheduled on a CPU taking the place of another one. Obviously, that's going to happen many times per second, so you end up with a lot of events. So whereas a logger will deal with a couple events per second at most, we deal with thousands of events per second. So that means we must lower the cost per event, and that means we have to use binary formats, and that means you need to use either graphical viewers or, in the case of Babeltrace, a command line tool to decode the log. And traces are harder to work with than text log files, because obviously we're producing a lot of events. Files are going to be huge, typically. So that makes the exploration difficult, and that's why we want to build our own tools or use tools that are made to track some things in the kernel from those traces. LTTng, which is the tracer on which I work, LTTng stands for Linux Trace Toolkit Next Generation, and I'm not ever going to pronounce that again during the talk. It started off in 2005, so it's quite old at this point. It regroups a number of projects, but basically it's a collection of tracers that are unified by the same configuration tools. The main difference between LTTng and other tracers is that we focus on being usable in production. So the goal is to trace applications and the kernel on production systems and not just on dev machines or staging environments to debug a specific problem. So we have to focus on reliability. Everything is built out of the process of the applications. So the applications are just going to be writing to shared memory, and the rest happens outside of the application. So basically, if we make a mistake and LTTng crashes, you don't lose anything. You lose tracing, but you don't bring down the system or the applications. And dynamic configuration means that if you want to enable events or disable the tracing of certain events, both in the user space and in the kernel, there's no need to restart your kernel or patch your kernel or restart applications and so on and so forth. Sorry. And the last point that's going to be important for the demo is that since LTTng has many tracers, we want to unify them. And so the nice thing is that you'll be able to see kernel events events from C, C++ applications, Python, Java, all on the same timeline. So if you have a Java application that's talking to a Python server using IPC mechanisms, you'll see them both on the same timeline interacting without having to shuffle around different files. User space tracing, as it relates to kernel tracing, is usable as a high-performance logger. But the thing is that the most useful thing as far as user space tracing is concerned with the kernel tracing is that it provides anchor points. You can see, okay, my application did this, it served this request, and this is what happened from the kernel's point of view. So then you can make sense of what happened in the kernel, rather than looking at just kernel events and saying, okay, I'm seeing that the kernel's doing something, but why? I don't know. So the user space tracing answers the question why something's happening in the kernel. I'm going to show how we can instrument a Python application, since this is PyCon after all. We provide the LTTng UST Python agent that basically hooks on the standard logging mechanisms of Python. So that means that we support both Python 2 and 3. And basically, you just need to import LTTng UST, and that's going to set up a log handler that funnels everything that your pre-existing Python application logs down to the LTTng buffers. So that looks like this. If we want to instrument the standard LTTng, not LTTng, Python simple HTTP request handler, I'm basically just deriving from the simple HTTP request handler and overriding a couple of methods. That's then, yeah. Oh, bigger? All right. Is that better? All right. Bigger? Okay. But basically, the only LTTng specific line in this whole file is the import. The rest, you may know that the simple HTTP server just logs onto the console, so I'm just overriding the methods to funnel that through the logger. And that's what I'll be using for the demos. And actually, I'll start off to show you how we would enable Python tracing. Is that all right? Okay. So that's the logging, basically the script to, ooh, bit of problem of safe area here. Let me see the side of the screen. Okay, but basically we're setting up a session, and that's just creating a session that's called PyLogging and enabling all Python events and starting the session. And that's a live session, so we can hook onto LTTng to see the events as they are produced. And if we perform a request, you'll see all the, hopefully, you'll see all the Python events coming in. Yeah. So basically now you just have your regular Python logging messages in a LTTng trace. And this is Babeltrace's output, so that it's very generic output. Basically, we just have the event name, a couple of context fields, like on which CPU that happened, and the rest is really from Python. If you look at the message field, you basically have your logging string directly in the trace. So we got the same as we had before. That's fine. The nice thing is that we can add kernel events to that. And that's where stuff starts to get interesting. So again, we set up the session the same way. Just this time it's called py syscalls. We enable all Python events, and we enable all the syscalls that are available for the kernel tracer. And next you'll see that if I do LTTng view, you start seeing the syscalls, so the Python server is basically calling poll on one FD, and whenever something happens, it unblocks, and it's going to serve that request. And then you can see all the system calls that it takes to serve that request. So that's fine, but really at that point, you have to know what you're looking for, really, because that's a very generic view, and it can get pretty hard to read. So this is where Python comes in very handy. We need better views. And thankfully, I mentioned LTTng started off in 2005, and we introduced the Python bindings in 2013. So during that time, what were people doing? They were using the text traces and piping that through a mess of bash commands to try to make sense of the traces, as you do. But that ends up being unmaintainable, and people were passing off scripts to each other, and then we would add an event, a field to the events, and scripts would break all over the place. So we finally introduced those Python bindings, and a lot of people are starting using that. And I guess I don't need to sell you the benefits of Python, but I mean, things are reasonably efficient. With LTTng, you can enable every event in the kernel, so that's going to be thousands of events. Of course, that's going to take some time to process. But if you're careful about what you enable, it's manageable. It's not going to be too bad. So people were building analysis for their applications, and we saw a couple of neat things. People were tracking connection pools, thread pools, memory usage, those kind of things. So it's kind of nice. And we wondered, well, what we could do, we can't produce tools for your applications because we don't know them, but we can provide some tools out of the box for Kernelspace. And that's why we started off with LTTng analysis. I'm not going to demo that because basically I did another talk at LinuxCon. You can watch that, and all the scripts are available on GitHub. But LTTng analysis allows you to see during a given time span which syscalls were made, how long they took on average, what's the median, the standard deviation, which errors occur, and when. You can see, well, during that request which went wrong, what was the I/O usage of each and every thread. So you can really search for clues in your trace. So it's never going to give you an answer as to what went wrong, but it sort of helps you dig down into that. What I want to show you is how you can start a new tool from scratch. So the nice thing that I like with Python is that I can just say, if I could see this, I'd be able to debug that problem. So you can just go ahead and work with the trace. And you'll see what I came up with for this talk. Again, performance can be a concern, but you'll see that today we won't be enabling that many events, and still we can get a lot of information for our script. What I'll be using is the new version of Babeltrace, and that's going to be released by the end of the year. Right now, we're in the release candidate stage. But basically, what this allows you to do is combine pre-made components and assemble them to craft a trace analysis pipeline. Those that are there are some that come out of the box with Babeltrace. And what I'm going to do is implement the last one, the sync, in Python. And so you can mix and match the components that are implemented in C, C++, and Python, and it doesn't really matter for you. We'll see a kind of call stack view. It's a bit inspired by uftrace. But basically, I'll be using a CTF source because everything, now we'll have kernel events, we'll have Python events, and they all get serialized as CTF traces, LTTng's format. We'll mux all of those together, so they end up on the same timeline, they use the same clock source, and we can figure out which events happen in what order. We'll inject some debug information. I'll show you that's going to be useful only for the last demo. But then our plugin's going to handle all the events that come our way. So if you want to implement your own analysis or your own tool, you implement a Babeltrace plugin, and that sounds scary, but it's not too bad. Basically, you just have to implement 2 methods from that generic class, BT2 user sync component. That's port connected, so you're part of a graph, and then consume. When we get connected to a port, we can just subscribe to event notifications, pretty straightforward, and then start consuming events. So every time we get a new event or a new notification that an event is available, we can check the name and do something with that event. So if we still use the same trace that we had, so remember that we had all syscalls for our HTTP server process, and we had all Python events. We can combine those. And then we see the actual syscall being made. And you can see that Python actually polls and unblocks every 500 milliseconds. And then if we do a request, we're going to see both the Python logging statements and the syscalls in different colors. I'm going to stop that so we can scroll a bit. But basically, let's find some requests that failed. You see the beginning of the request, and then you see everything that the Python interpreter has to do in terms of syscalls to handle that request. And of course, you can always look at the man page of each of those syscalls if you're not familiar with them. But basically, we're retrieving some information about that file, and the kernel is returning an error, which is why it's in red. And then we try to open that file, even though it doesn't exist. So we get the same error again. And then we return to the client that code 404, resource not found. And so on and so forth. So really, the nice thing here is that if your application is too slow, you can see where you're losing time. But at that point, it's kind of hard to say, well, OK, obviously I lost some time between the send to and the write. But what does that map to in terms of the actual Python code? This is where there's a patch set that we proposed for inclusion in CPython. And we want to instrument the Python VM. And I think there was a good reception for that. The only thing that's sticking is the naming of the event, so that should be resolved fairly soon. But if we use the LTTng list command, we can see what events are available before we enable them. As far as the kernel is concerned, you can see that those are all events that are not syscalls, so those are internal subsystem events. That's running on a mainline kernel. You don't need to patch anything, by the way. But again, if you were looking for let's find something interesting, block layer events, you could enable them. Same for net, same for memory management events. We can focus on system calls. But now what I wanted to show you was what's available as far as user space is concerned. And we see that we can track every garbage collection cycle that starts and when it's done. But the new thing here is function entry and function return and Python line. So you can have every entry and exit in a Python function along with your syscalls. So what this allows us to do is to see the call stack evolve over time through your Python code and then see how that code ends up calling system calls. Again, we're building up on the same example, enabling all Python events, enabling all syscalls, and just enabling function entry and function return for the Python interpreter. Now, that view starts to make sense. So you can see that this is a loop within the HTTP server, serve forever. You have the name of the file and the line number, and you see the syscall being made. And now you get a lot of information. But that's just serving the main, the home page of LTTng. So you see all, well, basically every request for a file on that page as separate requests. You see everything that's involved in that. So I'll try to start with a begin get. So we're starting off with this, and then we see all the Python code that's involved. Basically, do get, send add, translate path, and that's where we change the working directory. The new stat that we had is done by the isdir in Python, and that's not handling the error that the file doesn't exist. So of course we could abort there and just throw an exception and return 404, but the code keeps going on until we reach openat, and then we realize that there's something wrong, and we send an error all the way to the actual 404 message that's being written on the socket here. Until we have to serve another request, and so on and so forth. I should mention at this point that I've been using the live mode, but you can always save that to disk and work on it later. But also, the other one, nice mode that we have is flight recorder mode. So basically, if you think of a plane, you have that black box that's now orange, I think. But basically, you're recording the last few minutes of action, and you're never touching the disk as far as LTTng is concerned. So you're just in RAM, so there's very little impact. And when something happens, say you have a 404, and you want to capture that, you can just issue a LTTng snapshot record, and then you'll just have those few megabytes of trace data, and you can run them on your machine. So you could collect those in production, and then on your development machine, have all the call stack and see everything that went wrong up to that point. And finally, maybe I can show the code that's involved in that. But basically, on every entry and exit, we're basically just incrementing the indentation level and printing the time. And printing the time is actually the longest part of that script. With all the colors and unit conversions. I'm not going to focus on that, but that's going to be on my GitHub. But the rest, when you want to handle a syscall in your tool, basically just get the event name, and then you can iterate on the payload of the event. And that's just what I'm doing. So I'm printing the event name, and then going through all the fields and appending them side by side. And that gives you all the information that you need to debug that. So it's really, we try to make it very simple. You don't have, even though it's a binary format, I don't like binary formats more than any other one, any other here, I guess. But I want to make that as easy as possible to use. Now the last thing that I want to show, and that's a bit cheating because I had to recompile my Python interpreter, but just to show you that it's doable. Basically, if you compile your interpreter with f-instrument function, that's a GCC option, you can add instrumentation inside any entry in a function and exit. So basically what we had with the Python code, but you can get that with C code. So now we can see the Python code, what it calls in the interpreter, and what the interpreter calls in the kernel. And you'll see that that's way too much information. So again, the same example with the same server running. You'll see that I have to enable a bit more stuff, but that's basically just tracking what's the PID of what I'm tracing, and IP, that stands for instruction pointer. So that's the address of the code that was running at that time when we traced. And the rest is basically the entry and exit in C code. And once we have that, we can hook again in live mode, and we'll see the same thing as before, except that we can't resolve the symbols because we just have the IPs. But you can force LTTng to dump to the trace the base address of all the binaries that are involved. And then you'll get every function call in the Python interpreter. And those green bits that you see fly by are the actual Python code that's being called. Wait until you see a request coming in. That keeps overflowing, but the stack is... So that's more like it. So you can see the indentation level of that stack. So that's too much information to work with, except if you're debugging the interpreter, I'm sure that can be useful. But I'm not sure I captured everything. Well, we won't see the end. But that's another thing. Your tool doesn't have to keep up with the rate of production of events. So LTTng is going to send you that gradually as you can handle it and buffer to disk in live mode. So you can see that we're falling way behind because those are microseconds and nanoseconds. So we're seconds off, and the request has long since been completed. We're not slowing down the HTTP server at that point. But the viewer is falling behind. And so that's all I have.